everyone, my name is Lyron. I work at Seismic, and today I'll be talking about how we built interactive fog of war for network states. Today we're going to start off with a demo, and then we'll go into a little bit about how we did it. First, starting off with, our live demo here. Okay, so for those of you who don't know, network states played on a 2D grid. The premise of the game is that you spawn onto this grid with a set of troops. You're supposed to use these troops to conquer tiles that are around you. As you conquer tiles, you start to be able to see more. You can only see one tile out from all of your conquered tiles. As you can see here, with the blue, you can see some gray area around. And as you keep conquering, you expand your field of view. In this example, we have two players that are inhabiting the same region. Even though they're inhabiting the same region, they can't see each other because they're covered in fog of war in their respective clients. As you can expect, if you move the player on the left, right one, we can start to see what's happening. They start bleeding into each other's peripherals, and this is exactly the fog of war mechanic that we'd like to emulate. And in here, not emulate, this is actually on running on a blockchain, fully on-chain, it's all there. So with this, we don't want to just be able to see, we also want to be able to modify. So more than just seeing green's tiles, you want to be able to conquer them. And on blue's left here, you can start conquering into greens. And so that's the first part of fog of war, and that's introductory. That makes sense. Here's the cool part. One of the main tenets of on-chain games and on-chain worlds is that they exist whether or not you're looking at them. So here is what we'll do. We're going to log off on blues, shut off the terminal, shut off everything, and the main thing that we wanted to enable with this build was that even though blue is offline and couldn't hold down their own state, green can still come in and keep seeing more of blues. More importantly, if we keep moving green to the left over here, we can keep conquering blue's tiles. And so this is important. It creates a feeling of blue leaving the game and the world persisting and being something that lasts, and no matter what, no matter who's online. And so thank you. Yeah. So what we have here is a fully on-chain world where you can log on, you can add state that belongs in fog of war, you can log off, and then you'll have this state persist and interact in the way that the game makers intended. So that's our live demo. Let's talk a bit about how we did it. Okay, so how did we do this? Let's start off with the example board, and this is where most of our explanations are going to stem from. We'll first start off with a representation of this board on-chain. We'll go through how we move it, and then the details on how everything actually works. This is a sample network states board with a blue team and an orange team here. If this board was just on-chain, then there would be no fog of war, because then you can ask the chain what's happening on every tile, and the chain will tell you. So instead of keeping this representation on-chain, we keep this representation. What we do is we run a cryptographic hash function in each tile through a cryptographic hash function to get a jumble of numbers and letters. This jumble has two special properties. Number one, you can't go backwards. Given a jumble, you can't tell what tile produced it. Number two, these jumbles are also binding. You can't change the underlying tile without changing the jumble as well. That's why these are called hiding commitments. Hiding because you can't go backwards, and commitments because you can't move the underlying state without moving what's happening on-chain. And so this is why this is a good representation of some hidden state that should be on-chain. It's a jumble of letters that you can't tell anything from, but is binding, so you can't change the state and cheat from it. So we have this representation. How do we use it to actually move and reflect what's happening with the game? For that, we're going to go back to our visual mode. And let's look at, on the top right, with the 9 orange troops. We want to take these troops and move down one. What does that actually look like? Let's go back here. What we end up doing is we take the two commitments that correspond to these tiles on-chain, we consume them, we throw them out, and then replace them with new tiles. And that's exactly it. The way that you can think about this is that each commitment corresponds to tile state. Whenever tile state changes underneath it, the commitment is now stale, needs to be thrown out, and needs to be replaced with a new one. And whenever you do this replacement, you also have to submit a zero-knowledge proof to say that you did this replacement honestly. You didn't just move 9 troops and get 50 troops on the other side. So really, this is exactly how movement works, how representation works. And I'm not lying when I say it really does not get more complicated than here. Hopefully in the last 2 minutes, you got 80% of how we actually represent hidden state on-chain and how we can modify it. And then now we can get into the details of how this is actually done, because there's some nuances here, but not many, I promise. So first off, we're going to start off with the game requirements before getting into the details. This is what we did with network states. We started off with what user experience, what player experience we wanted to provide, and then we built a crypto system around it. First off, on the requirements, we have number one, these worlds are going to end up meaning a lot to a lot of people. They'll store a lot of value that means a lot to people. So you don't want game state to be easily manipulable by malicious parties, whether they're operators or players. We want game state to be honest. That's a hard requirement. Number two, we want the gameplay to be smooth, even when the game is massively multiplayer. Network states one day wants to support tens of thousands of players that are playing at the same time. Communication and computation complexity should scale sub-quadratically with a number of players, or else the game is slow, the gameplay is not great. It needs to be efficient. And then third, as we demonstrated in the demo, we want this feeling of being able to go online and offline wherever you want, and it's like you're entering a world and then leaving a world after it. So these are our 3 gameplay requirements, and they're surprisingly, really incredibly difficult to hit all at the same time. And so we'll first start off with what didn't work. What didn't work were solutions that were based on pure ZK, pure FHE, and pure MPC. If these letters don't mean much, that's okay. They didn't work anyway. The main principle of why they didn't work is because shielding isn't interactive. You have fog of war from one player, fog of war from another player. Whenever fog of war from player A wants to walk into fog of war from into player B, like conquer their troops, there's a barrier there when you're using pure solutions, and you can't do this verifiably. And that's why none of these pure solutions didn't work. So what did we do? We mixed and matched. We got little bits from each of these pillars of cryptography, and then we stitched them together into some end-to-end system that hit all of our requirements for gameplay and had a security model that we're comfortable with. And at the end of it, we're really proud of this result. It's relatively easy to understand and build. We care about building games in the next few months, not the next few years, with a team of 8 PhDs who are spinning up a custom multi-party computation protocol for you. We care about this a lot, and we hope this is going to come through in the presentation when we talk about the construction. And without further ado, this is it. So we have the chain, which is the source of truth for the game, and then we have Alice. Alice is a player. This is how typical on-chain games work, and now this is what we're adding. We're introducing a server. And I know this is a terrible start because servers are bad words in the blockchain community, but bear with me here. What we're doing right now is we're introducing an entity into the system, and then we're stripping this entity of as many trust assumptions as we can until only the bare minimum is left with it. And so we introduce an entity, make it pretty much powerless, and this entity ends up contributing to a system that delivers a great gameplay experience. So here's what happens. This entity is going to keep, the server is going to keep the actual state of what's happening in the game. It's going to keep the numbers and who's where, what's where. The chain, on the other hand, is still going to keep track of the commitments. Whenever you're reading the chain, anyone can see the chain. You still should only see the jumbles. What this entity is going to do is it's going to bridge knowledge from one player to another. Whenever Alice moves, Alice first tells this entity what Alice is about to do. Then whenever Bob comes in and gets close to Alice, Bob says, hey, server, I'm close to this person. You can see that by what's happening on chain. Please tell me what's going on there. And once you tell me what's going on, then I have enough to construct a zero-knowledge proof to transition Alice's state. This is crossing the boundary that we talked about earlier. There's this wall between Alice's and Bob's state. This server is what lets you bridge between the wall and transition state between it. And that works in this flow. Number one, Alice uses the server to learn about its surroundings. Number two, Alice shares the next moves. And then number three, once Alice shares the moves, the actual move happens directly between Alice and the chain. There's a ZKP for the state transition. This is taking the old commitments and adding the new ones on. And notice that all the lines on the bottom are dotted, and the main one that matters is really the one at the top. That is what determines game state. That one must be secured by purely cryptographic or proof of stake trust assumptions, and that's a core part of our design. And then number four, the server doesn't trust Alice whenever Alice says, I'm going to move to this tile. The server runs a light client to see. did Alice actually move? And then it updates the internal belief system. So what all this comes together to create a server that's really weak. So really, there is a reason that servers are bad words in the community, and this entire design is towards making the servers as powerless as possible. There's 3 things that you need to make sure to do when you're doing this. This is a delicate matter, introducing an entity to hypercharge your system. You don't want to give it too much power, or else all of the properties that you want in a blockchain game all go away. So the important things you should never do. Like, you should never run logic on the server. You should never release a server without any data extradition capabilities. You should never do any ordering on the server, so it never is responsible for anything in the MEV pipeline. And there's a long list of these. I won't go through each one because there's a lot, but the important takeaway here is that if you insert the server really carefully, you can create a great gameplay experience that doesn't compromise on all of the properties of blockchains that we want to uphold. And these properties are here, but oh wait, not yet. Before I talk about the properties, can I go backwards? Oh, I see the backwards button now. Before talking about the properties, this is the end result of this. State is still very much on-chain. Truth and game truth is still very much on-chain and enforced via cryptography and proof of stake. A copy of all state exists in the server. That's the upshot of this entire presentation. And this meets all the requirements that we set out to meet. And when I tell you, we went through more than 10 solutions that used many corners, many techniques from the corners of cryptography to do it. And this was the only one that hit all of our requirements, that had a security model that we were satisfied with and that we were okay giving to players. And more importantly, we ended up with something that was pretty simple, that we could build and ship because we care about that the most. And then other people can also integrate into their systems because it's a generic construction that's easy to build and doesn't need 8 PhDs to figure out. And so I want to end off with a security model here because this is of the utmost importance. I want to emphasize that all of the properties that we use and we enjoy for blockchain games today, like provenance, infiniteness, self-custody, and so, are relatively untouched as long as you follow the guidelines for what explicitly not to do with this entity. And that's good. There are a lot of buzzwords. What that actually means is that if many parties in the system are malicious, operators, players, if we had a catastrophic event where so many people turn malicious, there are a few things that still cannot happen. Number 1, malicious people can't invent troops out of nowhere. Number 2, they can't steal land. And number 3, they can't delete capitals. And this is great because what this means is that now if you want to interoperate with this game, you can build an entire game in one of the tiles. And you know that tile is never going to get rugged because that's secured by cryptographic trust assumptions. Or hopefully it never will. It's a big deal if the cryptographic trust assumptions go away. But really, it should never happen. Another thing that you can do is you can put money into the game. When I talk about all these on-chain worlds actually storing value, it's both economic and sentimental value. Economic value that you put in, and if you stake something on a tile, that tile is never going to get rugged from you, and your money's never going to get rugged, because again, that's fully cryptographic and proof of stake. It's not a perfect world by any means. We still have a server, and we need to be careful about this. The server still has the trust assumption on shielding. What we've done here, essentially, and the principle that we'd like to start talking more about in the AW community, is we should list out all of the properties that we want for blockchain games and tease out exactly what we care about. Whatever we really care about, let's throw it on the left. Let's throw it on the left, because on the left is the green zone. Whatever we can't, we need to be really clear about this and be really careful about this because we know what we need to focus on. And on the right, this is the last thing that we couldn't throw on the left yet. This is still very bad for now. It's a security model that we're okay with in the short term because of so many things being on the left and so many things that we care about in the game is on the left. But shielding is most definitely still kept by the server. If the server knows all, you usually run these in trusted hardware modules, so you can't easily get into them. But because of the existence of side channel attacks, you should really just think about it as a server because there are ways to break things if you put enough money into it. It's still very hard, but it's doable. So that's still bad. There's a way to make this transition to the left side. And long term, this is exactly what every game should do. This is what we're working on full time at Seismic. We want to hit that on the left side. We're going to talk about this more in future talks. And then finally, we also want to be accountable through every step of the way. We want to be very clear about what we don't have. What we don't have enclaves right now. If whenever you play network states in the next week or two, the network states team will be able to see everything that's going on. That's for debugging. That'll go away soon. We also don't have an independent DA layer. We do run DA, but we run DA ourselves. That's not great. That should be independent. We also don't have any multi-party computation at all. This is part of the path to doing it in a very particular way to get shielding to be fully decentralized as well with minimal trust assumptions. We haven't written a single line for that. That's very difficult because doing this was already a lot of work to get to. And then finally, we don't have any terrain. Our terrain broke the other day, so the demo just had no Perlin noise in it. That'll be back in soon. What we do have, though, is we have a game with a good game experience with acceptable trust assumptions and generally is a fun game, which is the important output of what we wanted in the past few months of work. And then finally, as I said earlier, this is a construction that works for many games. The three requirements are things that are not particular to network states. The fact that you can't break the world, the fact that you want the world to scale to massively multiplayer worlds without having to wait 9 seconds, 10 seconds per construction, and then like the other properties that we listed today. So important to note that all of our code is fully open source. We have no business license in any of them. All of our docs are also public. It would be really cool to see everyone implement this into their own game whenever they want some sort of interactive fog of war that has a good gameplay experience. If you have any questions while doing this, please feel free to reach out to l@seismic.systems. And then finally, some acknowledgements. Thank you to the network states team for letting us collaborate on their epic game. Thank you to Mud for developing a framework, the Mud team for developing a framework. That was great to work with. And finally, thank you to our predecessors who have applied cryptography in the application layer to create fun game mechanics. And we've learned a lot from them. So Dark Forest, ZK Hunt, ZK Dungeon are some great predecessors that we really enjoyed. So thank you, everyone. This is the presentation. I'll end off with a discussion question. I'll just leave it here. And that's it. Thank you for listening, everyone.